Okay, now we're going to talk about sample proportions. Proportions are just essentially sample fractions, or what percentage. So here I've got 210 out of 501. Remember my sample proportion, sample being p hat, population being p. Proportions should always be essentially percentages, so they're always between 0 and 1. So we can think of our sample p hat as the count of successes in the sample versus divided by the sample size. And this is really important formulas. They're going to show up in some boxes later, but I'll just highlight them right here. The sample mean is then n times p. The sample standard deviation, if I'm given a proportion, is square root of n p times 1 minus p. So, sampling distribution of a sample proportion, choose an SRS of size n from a large population with population proportion p having some characteristic of interest. Let p hat be the proportion of the sample having that characteristic. Then the mean of the sampling distribution is exactly p. It's unbiased. The mean has to be equal to the mean of the sampling distribution. And the standard deviation is equal to the square root of p times 1 minus p divided by n. Okay. However, in order for this to be true, we have to check a few things that are called rules of thumb, because these are only true if these assumptions aren't valid. Use the recipe for standard deviation of p hat only when the population is at least 10 times as large as the sample. So that means if my population is 80 high school boys at Alturas, I can't use this formula if my sample size is 30. Doesn't work. My sample size would need to be at least 300, or my population size would need to be at least 300 for this to work. My sample size were 8, which is really kind of small. I suppose this could work, but kind of key that your population be at least 10 times the size of your sample. So again, high school boys at Alturas with 80, that can be at most 8. Okay. If I want a sample of 30, I would need a class or a high school with at least 300 boys in it. Okay. So that is the sample proportion. We can approximate sample proportions to normal very often if they satisfy rule of thumb number 2, or this condition that says NP is greater than or equal to 10. P being the probability of what we would call success. So NP, there needs to be at least 10 or more in my success group. And N1 minus P also needs to be 10 or more. So we have these kind of key rules. This I would call the size of success group. This here I would call size of fail group. So the success and fail group each need to have more than 10. If it's really slanted one way, you could have a really big one, but you need to have at least 10. So if it's a 98% chance, I can do 100. I get 98 yeses. I only get 2 in the no. at least in the assumed no group size. That cannot be approximated to normal. It needs to have at least 10 in that no group size. So, applying to college, kind of important. All of you are doing that. A polling organization asked an SRS of 1,500 first-year college students whether they applied for admission to any other college. People didn't used to apply to 10 colleges, usually. Used to be you applied to a couple. There was no such thing as the Common App where you could fill out one application and send it to a bunch. You had to do distinct applications and separate essays for every place if you had to do essays. So this says, what is the probability that a random sample of 1,500 students will give a result within 2 percentage points of the true slope? We have an SRS of size 1,500 from a population with proportion p hat equals 0.35 applied to other colleges. The sampling distribution of p hat means that mu of p hat equals 0.35. What about its standard deviation? Well, using the first rule of thumb, 10 times the 1,500 in our sample, our population of first-year college students in America is well over 15,000. As a fact, there's 1.7 million, so we're good there. Rule of thumb number 2, and they do kind of show it lower, but I'm going to write it off to the side. NP, so NP has to be greater than or equal to 10. N being 1,500 times 0.35, and that is 525. Well, that's way greater than 10. And 1,500 times 1 minus 0.35, that's 0.65, and that's 975. Now I'll make that a little neater. And yes, that's also much greater than 10, so I can approximate this to normal. I know the standard deviation. P is 0.35, 1 minus P. Yeah, they just wrote out, they did 1 minus 0.35 to get the 0.65. Over 1,500, the square root of that is 0.0123. We're looking for the probability that falls within 2 percentage points. So that's between 0.33 and 0.37. So we're looking for something that falls in what's shown in the area of our shaded region. Okay. So now, step 1, standardize p hat. And I'm going to do it for both ends. So we take this, we plug in 0.33, and we get negative 1.63. We plug in 0.37, we get 1.63. The probability that p hat is between those, the probability that the z's are between these. I look up positive 1.63, I get 0.984. I look up negative 1.63, I get negative 0.0516, giving me 89.68%. Basically, with 1,500 college students, if my actual population is 0.35, I have almost a 90% chance of a sample of 1,500 giving me a proportion between 0.37 and 0.33. So giving me the proportion within plus or minus 2 percentage points. I don't know what I'll actually get, but I have a 90% chance of being within 2. That means if I get a result, I also have roughly a 90% chance. It goes into some calculations we'll get to in the next couple weeks. But basically, I have roughly a 90% chance but I am within 2. So I can go, if I got 0.36, I've got a 90% chance that the actual mean is somewhere between plus or minus 2 would be 0.34 and 0.38. So survey under coverage. One way of checking for survey under coverage, non-response, and other sources of error in a sample survey is to compare the sample with known facts about the population. About 11% of American adults are Black. The population proportion of Blacks in an SRS of 1,500 should therefore be close to 0.11. If a national sample only contains 9.2 Blacks, should we suspect the sampling procedure of somehow underrepresenting Blacks? Well, it's a bit low, but is it low enough that or was it just random selection? So what we can do, we can start by calculating our sigma. We know it's supposed to be 0.11. So we can plug that in for that is our P. We get 0.00808. We should check that we know that of anything, 1,500 is much less than our sample of American adults, way less than 10%. So we're good there. We have 165, 1,500 times 0.11 is 165, and 1,500 times 1 minus P, 0.89, 1,355. So rule of thumb 1 and 2 both succeed. Now, we are going to check our values by standardizing P. We're using this formula, and we can plug in for P hat 0.0902, this 0.11 over 0.00808. And oops, when we do that actual calculation, I'm going to go over to the next page where they actually do it. We get negative 2.23, and the probability being right here, 0.0129, about 1%. Something about this survey probably underrepresented Blacks. Now there's a 1.29% chance that it was just random variation, but that's not a very good chance. Okay. And we were just able to calculate that. We didn't have to know anything about how it was observed to calculate that. So that was sample proportions. This is sample means. We can do this same thing with means. So to check if we can use our normality and our z-scores, we have to check that rule of thumb 1 to use the sigma calculation to get standard deviation of the population. And we have to use rule of thumb number 2 to check if we can use the normal curve. Well, what if we have means and not proportions? What if we have a group of teenage boys and we say their average calories is 2,500? That's a mean, that's not a proportion. We could do a proportion of boys with more than 2,500, but that's not the question. So how do we know if we can use normal? Well, the central limit theorem becomes really important and really powerful here. So lots of populations are roughly normal, but few are exactly normal. There's also several that are not normal. Okay? However, if I choose a mean from a non-normal population, the means of all samples, so let's say my boy's eating is a pretty uniform distribution from 1,000 calories to 6,000 calories. It's probably not, but we'll pretend it is. The means, if I take a large enough sample size mean, which large enough is considered anything over about 40, if I take a group of 40, I take all the possible groups of 40, and I average their calorie consumption. The means of those will be approximately normal by what's called the central limit there. Again, I can have a very screwy shape. Let's say my density curve looks like this. If I randomly select 40 points from within this density curve and do all possible samples of size 40 or more, I should get a density curve of those means that is roughly normal. Not a density curve of the individuals, but a density curve of all the means of sample size 40 or means of sample size 50. What makes this powerful is now I can do calculations on the probability of the means. Again, it's not the probability of any individual value, it's the probability of the sample mean, which allows me to draw conclusions about the population mean. So here we're going to see an exponential distribution. Notice it is curving down, okay? Nothing particularly about that. That doesn't look remotely normal. If I take sample size 2 and do all possible samples, that still doesn't look very normal. It looks very skewed right. If I take sample size 10, that kind of looks normal, but it's definitely still got this little bit of skew out here. At 25, it's a little bit skewed out there, but it's not skewed bad. All of a sudden, my sample means are starting to look pretty normal. So, servicing air conditioners. The time that a technician requires to perform preventative maintenance on air conditioning units is governed by the exponential distribution whose density curve appears to be in figure 917. The mean time is an hour and the standard deviation is also an hour. Your company operates 70 of these units. What is the probability their average maintenance time exceeds 50 minutes? So, the central limit theorem says that the sample mean time x bar on work spent at 70 units is approximately equal to the population mean mu, and hour equals 1 hour and standard deviation. So, standard deviation of 1 hour. We need to talk about what's called the standard error. I apparently did not scan this little section of the book. The standard error is sigma divided by square root of n being the sample size. So as my sample gets larger, standard error ends up replacing standard deviation in sample means. Standard deviation is the standard deviation for the whole sample. But when I start getting samples of samples or the distribution of sample means, they get tighter. And we saw that as the sample size got larger way back at the beginning yesterday. So this tightens up my standard deviation. Okay. So now we've calculated here our standard error, since I've got 70 units, is going to be 0.012. So using my z-score formula, I use my mean, my mu, and my sigma. So they have plugged in here. I want to know what's the probability of it being more than 50 minutes. They've converted 50 minutes to 0.83 hours by going 50 over 60. 0.83 minus 1 is this or is that's the population mean. And my standard error 0.120 gives me a negative 1.42. I'm looking for the probability. Sorry, I need to go back. I can't remember what the question's asking for. Is it asking for more than one? What is the probability their average maintenance time exceeds 50 minutes? So the mean is an hour. So I get z negative 1.42. That's gives me the probability of being below. That's that. So if I'm doing a sample of 70, 1 minus the 0.078 that's looked up in the z table is 92%. That is the area to the right of 0.3 under the solid normal curve. There's the exact probability. It is 0.9294. I think that's looked up with a calculator. The central limit theorem normal approximation is off by 0.007. And this is the actual right here. This is what we calculated with the normal curve. That's pretty close. There's a 92% chance that my average is going to be over 50 minutes. Okay. Again, we probably got these values of 1 with standard deviation of an hour from the manufacturer, and we were able to use them to calculate. We can have a 92% chance with our 70 units. That'll be over 50 minutes. Less, we would get actually more probability since that is below the mean. It's getting further from the mean. The more units we have, the tighter that spread's going to go. So we're looking at the tighter the spread's going to go on this guy. Hold on, let me clear this. Tighter the spread's going to go here. And this will make it less and less. That is the central limit theorem. That is the end of chapter 9.